Welcome back everyone. Today we will discuss about generation of alternating current. So in this diagram we can see a permanent magnet with north pole and south pole. The magnetic lines of forces, the direction of the magnetic lines of forces are from north to south. Okay. Now, these magnetic lines of forces, it is represented by B vector. Okay. Now, if you place a coil in this permanent magnet, this coil PQRS is a loop. Okay. If you place this coil in this permanent magnet, then the area vector, which is represented by vector A, it will act perpendicular to this coil. And as you can see in this figure, the direction of this area vector A and this vector B in the same direction. Okay, and this coil PQRS, it acts perpendicular to the surface. Okay, now the magnetic lines of forces that are passing through this coil, it is known as magnetic flux, right? So this magnetic flux, we can represent it as phi, which is the dot product of vector B and vector A. Okay, so we can write it as BA cos theta. Okay, if there are n number of turns in the coil, then we can write it NBA cos theta. Okay, now initially we assume that the coil is fixed in the permanent magnet, and at that time this area vector A is perpendicular to this coil. Now if we rotate this coil in the permanent magnet in the clockwise direction with a velocity of omega radian per second, this is a 3D diagram. If we represent it in 2D, then x-axis will be having this magnetic field vector B and y-axis will be having this coil. So initially the coil PQ is in this position. Now if it is, when it starts rotating, now let's say it is in this position. So if I want to calculate the angular displacement of this coil after time t, it is represented as angular velocity multiplied by time, which is omega into t. Okay. Now, since my coil is now in this position, as the area vector acts perpendicular to the coil, so in this case the area vector, the direction of the area vector will be in this direction. Okay, the direction of the area vector will be in this direction, as you can see in this figure. Okay, because my coil is moving clockwise direction. So after time t, we have already calculated the angular displacement, which is omega t. Now at this position of the coil, the area vector, it is acting in this direction, and if this angle is omega t, this angle will also be omega t. Okay, so we have seen the instantaneous flux from the previous equation, NBA cos theta. Theta is my angular displacement, so NBA we can write cos omega t. This is my equation number 1. So if I want to obtain the maximum flux, so that time cos omega t should be equals to 1. So if cos omega t equals to 1, so what is the value of maximum flux? If we represent it by phi naught equals to NBA, which is equation number 2. Now if we put this value of NBA in equation number 1, we will get the instantaneous flux phi t equals to phi naught cos omega t. And as we know from the Faraday's law of electromagnetic induction, the EMF equals to minus d phi dt, minus d dt of, we just put the value of phi over here, which is nothing but my NBA cos omega t. Okay, so if we take the derivative of this phi, what we will get equals to minus NBA d dt of this cos omega t. So it is minus NBA of minus omega sine omega t, or EMF is NBA omega sine omega t. So let it be equation number 3. Okay. Now when we will get the peak value of this EMF, when we will get this peak value of EMF, when this sine omega t equals to 1. Okay. So this peak value of EMF, if we represent it by E naught will be NBA sine omega t, NBA omega. Okay. Now if we put this value in this equation, what we will get? E equals to E naught sine omega t. Okay. So what is my current? Current will be EMF by R. Okay. So I will be equals to E means E naught sine omega t. So we can write I equals to I naught sine omega t, where I naught equals to E naught by R. So if we summarize the equations that we have got so far, so this was my instantaneous flux phi t equals to phi naught cos omega t, where phi naught value is, it is the maximum flux that we calculated, it is NBA. Then EMF equals to E naught sine omega t, where E naught value we found as NBA omega. For current, I equals to I naught sine omega t, so I naught equals to NBA omega by R, because I naught we have already seen it is equals to E naught by R. Okay. So if we represent this EMF, flux and current in a graphical manner, how we will represent? My x-axis will be time, and first in y-axis we will plot the EMF. Okay. So once we, how to plot this EMF? See, equals to E naught sine omega t. Okay. So when the sine omega t when we will at pi by 2 only sine omega t equals to 1, right? At pi by 2 sine omega t equals to 1, and we will get the peak value of this EMF. Okay. So if we draw a complete cycle of this AC waveform, this is my 0, this is pi, this is 2 pi. So at the middle 0 and pi we will get pi by 2, and at the middle of pi and 2 pi we will have this 3 pi by 2. So this peak value of EMF we will get at pi by 2. So E equals to E naught sine omega t. So it is a sinusoidal signal where it is peak value occurs at pi by 2. The positive peak occurs at pi by 2. Similarly at negative, its negative peak occurs at 3 pi by 2. Okay. Now next we can plot I equals to I naught sine omega t. If you notice this, EMF and current both are in the same phase. Okay. But I naught equals to E naught by R. So the value of I naught is less than this E naught. So I naught will be somewhere around here, less than the value of E naught, and it is also a sinusoidal signal and they are in same phase. So this red color waveform represents my current. Okay. Now come to this flux. How we will draw the flux? It is written as phi t equals to phi naught cos omega t. Cos omega t, how we can represent? Sine pi by 2 plus omega t. So we can also write it is sine omega t plus pi by 2. That means this is a leading phase. The flux is leading. Okay. The flux is leading from this EMF and the current. And so this blue color waveform, it represents my flux. So if you notice here, when the flux is maximum, that time my EMF and current are minimum. So when the flux is at 0, that time my peak, we get peak EMF and peak current. Similarly here at when I'm getting the negative peak of this flux, that time my both EMF and current are 0, and when I'm getting the 0 for this flux, that time I'm getting the negative peak of my current and this EMF. Okay. So this is how we can plot the EMF, flux and current relation over time.